The photograph looked like a smudge, a faint red thumbprint pressed against the black. Then the numbers came in, and the room went quiet. That smudge was a galaxy. It appeared to be sitting roughly 600 million years after the Big Bang. And by the standard model of how galaxies form, it had no business being that heavy or that massive at that age. Within weeks, more of them turned up. James Webb was built largely to confirm the standard story of how the universe assembled itself. Instead, in its very first years of operation, it started handing cosmologists a series of measurements that standard models struggle to explain cleanly, and the field has spent the time since arguing over exactly how serious that struggle actually is. I want to walk through this carefully, because there are two very different versions of this story circulating right now. One version, the one that spreads fastest online, treats this as a cover-up, cosmology quietly collapsing, while institutions keep smiling for the cameras. The other version, the one that's actually happening inside peer-reviewed journals, is messier and honestly more interesting. Real tensions that are genuinely unresolved, sitting right next to earlier, more dramatic claims that follow up observations, have since walked back. Both of those things are true at once, and separating them is the whole point of what follows. Let's start with what the standard model of galaxy formation actually predicts, because you need that baseline before any of this makes sense. Under lambda-cold dark matter, the framework that's dominated cosmology for roughly 40 years. Galaxies build up gradually and hierarchically. Dark matter first clumps into invisible halos through gravity alone. Gas then falls into those halos. That gas cools slowly, and only a fraction of it, generally estimated somewhere, in the range of a few percent up to around 20% in any given period, actually converts into stars at any one time. That ceiling isn't an arbitrary assumption. It comes from decades of observation, from star formation laws tested across thousands of nearby and distant galaxies, from the physics of how radiation and supernovae from young stars push back against further collapse and effectively put a brake on the process. In 2023, a team led by astronomer Ivo Labbé published a paper in Nature describing a set of red compact objects identified in James Webb's earliest deep images, appearing to be extremely massive galaxies, existing only around 600 million years after the Big Bang, with implied stellar masses in the range of tens of billions of solar masses. If those numbers held up, exactly as first estimated, some of these objects would have required converting close to all of the available gas in their dark matter halos into stars almost immediately, well beyond what the standard star formation ceiling allows. Astrophysicist Michael Boylan Colchin at the University of Texas published an influential paper the same year with a blunt title, Stress Testing LCD-M, with high redshift galaxy candidates, making the case that if these mass estimates were correct, they would represent a genuine and serious challenge to the standard cosmological model. That's the real documented starting point of this story, and it's worth sitting with, because it's a legitimate scientific tension, not a manufactured one. But here's the part that tends to get left out of the more dramatic retellings. A meaningful share of those original, most extreme claims have since been walked back or substantially revised, precisely because scientists did exactly what science is supposed to do when faced with a startling result. They went back and checked it more carefully. One of the most cited early candidates from that 2023 wave, an object catalogued as Sears 3210, was initially reported at a very high redshift consistent with existing extremely early in the universe's history. Follow-up spectroscopy using James Webb's NIR Spec-I instrument, which measures light far more precisely than the initial broad color imaging used to first flag these objects, found that it was actually a much closer, lower redshift active galactic nucleus, essentially a feeding supermassive black hole that mimics the color signature of a distant massive galaxy when viewed only through broadband imaging. That's not a minor correction. It's a direct demonstration that some of the most eye-catching numbers from the earliest JWST headlines were photometric estimates awaiting confirmation, not settled measurements, and that when spectroscopic follow-up arrived, at least some of them dissolved. More broadly, later work incorporating James Webb's mid-infrared instrument alongside spectroscopic redshift confirmation has systematically revised many of these original stellar mass estimates downward compared to the first photometry-only numbers. That doesn't mean the puzzle vanished entirely. It means the puzzle is smaller and more precisely defined than the first wave of headlines suggested. Some genuinely surprising, massive early galaxies have held up under spectroscopic scrutiny. Astronomers Stefano Carniani and colleagues confirmed two luminous galaxies at extremely high redshift in 2024, existing only around 300 million years after the Big Bang, with spectra clean enough to indicate their genuine stellar populations, rather than active black holes in disguise. So there remains a real, still unresolved question about how galaxies this bright and this evolved could assemble so early. But it's a narrower, more carefully bounded question than the model is being dismantled piece by piece. And the field's own literature reflects that narrowing directly through an entirely normal process of proposing a striking result, testing it harder, and updating the picture accordingly. Now, alongside the galaxy mass question sits a separate and in some ways more genuinely puzzling observation: galaxy shape. Under the older picture, astronomers expected the very early universe to look chaotic: irregular blobs, clumpy ongoing mergers, structures still figuring out what they'd eventually become. That's what earlier deep field images from Hubble had generally prepared researchers to expect. Instead, James Webb has identified a meaningful number of orderly rotating disk-shaped galaxies at redshifts corresponding to less than 750 million years after the Big Bang. Work led by astronomer Christopher Consolis and collaborators in 2023 found that classic Hubble tuning fork morphologies, spirals and disks, and more mature structures were already present earlier in cosmic history than standard models anticipated. Separate radio observations using the ALMA array have confirmed cold, smoothly rotating gas disks in some of these early systems, structures that generally take a long time to settle into stable, ordered rotation rather than forming instantly. This is a real, still active area of tension in the field, genuinely discussed as surprising in the literature, though it's worth being precise about what surprising means here scientifically. It suggests galaxy formation timelines and merger histories in the early universe may need real revision and refinement, not that the entire framework of hierarchical galaxy assembly is being abandoned. Models are already being adjusted to test whether early feedback from young stars was weaker than assumed, whether the very first generation of stars formed with a different mass distribution than later generations, or whether some other mechanism let gas settle into ordered rotation faster than current simulations produce. None of those adjustments have fully closed the gap yet. That's an open, legitimate scientific problem actively being worked on in real time, which is a different claim than saying nobody has any idea what's going on. Now, to the part of this story that is genuinely the most striking: black holes that appear to have arrived already fully grown. In 2023, a team led by astronomer Akos Bogdan combined James Webb and Chandra X-ray observatory data to identify an object called UHZ1, a galaxy hosting what appears to be a supermassive black hole with a mass in the range of tens of millions of solar masses, at a redshift corresponding to roughly 470 million years after the Big Bang. Alongside that came the identification of a broader population nicknamed little red dots, compact reddish objects, many showing signatures consistent with actively accreting black holes weighing millions to hundreds of millions of solar masses, sitting inside host galaxies whose overall stellar populations seem too small to have produced or hosted them through standard formation channels. Here's the comparison that makes this genuinely strange rather than just technically strange. In the nearby present-day universe, a galaxy's central supermassive black hole typically weighs somewhere around 0.1% of the galaxy's total stellar mass, a ratio that's held up reasonably consistently across large surveys of local galaxies, including our own Milky Way. In some of these early JWST identified systems, that ratio appears to run far higher, in some analyses reported as high as several percent or more, potentially close to 2 orders of magnitude off from the local relationship. That is a legitimately strange result, and it's discussed as such throughout the current literature on early black hole growth. The challenge is a matter of timing and physics. The Eddington limit describes the maximum rate at which a black hole can pull in surrounding matter before the radiation produced by that infalling material pushes back hard enough to choke off further accretion. Standard models generally hold that stellar mass black hole seeds form from the collapse of the very first generation of massive stars, growing continuously at something near that Eddington limit would need on the order of 1 billion years to reach the kind of masses being observed in these early systems. But James Webb is finding black holes at these masses in less than half that available time. That's a real, well-documented tension between observation and standard growth models, not an exaggeration. Several proposed solutions exist, and it's worth naming them honestly rather than treating the puzzle as unsolvable. Some early black hole seeds may have formed through the direct collapse of massive primordial gas clouds, skipping the intermediate step of forming and then collapsing normal stars entirely, which would let them start out much larger than a typical stellar remnant. Some may have grown through episodes of super-Eddington accretion, briefly exceeding the normal radiation limit under specific conditions that current theory allows for, but that haven't been directly, unambiguously observed at the scale required to fully explain the population. Some may involve growth histories more complex than simple continuous accretion, including mergers between intermediate mass black holes that current instruments haven't yet been able to directly detect on their own. None of these mechanisms has yet been confirmed as the full explanation, and each solves part of the puzzle while leaving open questions elsewhere. That is an active, contested area of astrophysics research right now, genuinely unresolved, and worth taking seriously as such, without needing to frame it as evidence the entire timeline of the universe is secretly wrong. It's worth being direct about one thing here. These black hole findings do not sit in isolation. They land on top of a set of other longer-running tensions in cosmology that predate James Webb entirely, and that are worth understanding on their own terms. The most well-known is the Hubble tension. Measurements of the universe's current expansion rate derived from the cosmic microwave background, the leftover light from the Big Bang, give a value around 67 kilometers per second per megaparsec. Measurements derived from nearby supernovae and other more local distance indicators give a noticeably higher value, generally closer to 73. That gap has persisted, and if anything, sharpened as measurement precision on both sides has improved, and Nobel laureate Adam Rees, whose team's work first helped establish the accelerating expansion of the universe, has publicly described the situation using unusually strong language for the field, at various points calling it a serious and unresolved problem for cosmology. There's also a related but smaller discrepancy called the S8 tension, involving how clumped matter appears to be on large cosmic scales depending on whether you measure it from the early or late universe, along with longer-standing puzzles like the so-called missing satellites problem, where simulations predict more small galaxies orbiting large ones like the Milky Way than are actually observed. And underlying essentially all of modern cosmology sits the fact that, after decades of extremely sensitive direct detection experiments run in deep underground laboratories, specifically to shield them from background interference, no experiment has yet directly detected an actual dark matter particle, despite dark matter being required to explain roughly 85% of all matter in the standard cosmological model. None of this means the standard model is collapsing, and it's worth being careful about that specific framing, because it's where a lot of the more sensational retellings of this story overreach. What it does mean, accurately, is that lambda cold dark matter, while still by a wide margin the best supported and most successful cosmological framework available, currently has several genuine, actively studied points of tension, where predictions and observations don't cleanly align, and James Webb's early universe data has added real, substantive new tension in a couple of specific areas, particularly early black hole growth and, to a lesser and more contested degree, galaxy morphology in the most extreme mass estimates. There's a useful historical parallel worth drawing here carefully. In the year 1900, classical physics appeared essentially complete, with only a small, seemingly minor anomaly remaining, the so-called ultraviolet catastrophe, involving how heated objects radiate energy in a way classical physics couldn't correctly predict. That small anomaly turned out to require the invention of quantum mechanics to resolve, which went on to reshape essentially the entire technological and scientific landscape of the 20th century. It's a genuinely useful reminder that some anomalies that look small or technical at first turn out to matter enormously, and that scientific frameworks do sometimes need fundamental revision rather than minor patching. But it's also worth remembering that plenty of anomalies throughout the history of physics turned out to have more mundane explanations once measured more carefully, exactly the way the CR's 3210 galaxy candidate turned out to be a much closer black hole once spectroscopy actually confirmed its distance. Both kinds of outcomes are normal parts of how science actually works, and it's too early to know with confidence which category the current early universe tensions will ultimately fall into. It's also worth being fair about why public communication around this topic sometimes feels more reassuring than the technical papers underneath it. Space agencies operate under real, institutional pressures, dependent on public and government support to fund future missions. And there are structural reasons press releases tend to emphasize surprising or exciting framing rather than insignificant tension with the standard model, even when both descriptions are technically accurate for the same result. That's a real dynamic worth understanding. But it's a different, much more modest claim than saying agencies or scientists are actively concealing a crisis. The peer-reviewed papers making these tensions explicit are public, widely cited, actively debated at conferences, and are exactly the process by which this eventually does get sorted out one way or another. James Webb itself has real, hard operational limits that shape how quickly any of this can actually be resolved. The telescope sits at the second Lagrange point, roughly 1.5 million kilometers from Earth, and its useful lifespan is constrained by a finite supply of propellant, needed to maintain its position and orientation, with current estimates suggesting on the order of 20 years of operational life remaining. Confirming the exact distance and properties of any single distant, ambiguous object requires substantial dedicated spectroscopic observing. Time in the telescope's schedule is booked years in advance. Beyond a certain distance, roughly corresponding to redshift 15, individual stars within a galaxy simply cannot be resolved with current instruments, and a wavelength cutoff related to hydrogen absorption in the early universe imposes a hard physical limit on how much detail can be extracted from the very earliest sources, regardless of how long the telescope stares. The next generation of major space telescopes, including the Nancy Grace Roman Space Telescope and a proposed Habitable Worlds Observatory, are either not yet designed for this specific kind of resolution or are potentially decades away from launch, which means the honest expectation is that this particular set of open questions is likely to remain only partially resolved for a meaningful stretch of time, genuinely uncertain rather than quickly and cleanly wrapped up. So, where does that leave an honest summary of what James Webb has actually found? It has identified real, still partially unresolved tension in how quickly some early black holes appear to have grown relative to their host galaxies, a genuine and actively studied puzzle without a fully settled explanation yet. It has identified surprisingly mature, ordered galaxy structures earlier in cosmic history than older models anticipated, adding real pressure to refine timelines for how galaxies assemble without yet requiring the wholesale abandonment of the broader hierarchical formation picture. And it has added new data points to a set of longer-running cosmological tensions, the Hubble tension chief among them, that already existed before James Webb launched, and that remained, collectively, one of the more serious open problems in modern physics. At the same time, a meaningful share of the very earliest, most dramatic individual claims from 2022 and 2023, the ones that generated the most viral headlines about galaxies that shouldn't exist, have already been revised downward or reclassified entirely once better spectroscopic data came in, which is exactly the kind of self-correction a healthy scientific process is supposed to produce. Both of those things are true simultaneously. Genuine, still open scientific tension in specific, well-defined areas, and a track record of some of the most extreme early claims already being narrowed or corrected through normal scientific scrutiny. The honest version of this story isn't a hidden crisis being concealed from the public, and it isn't nothing to see here either. It's a real, ongoing scientific puzzle being worked through in public and peer-reviewed journals by researchers who disagree with each other openly about how serious it ultimately is, using the best instrument ever built for exactly this purpose. That process is almost certainly nowhere. Near finished, and the honest answer to what it will eventually mean for our understanding of how the universe's earliest structures formed is that nobody yet knows for certain, which is precisely why the observations keep coming.